Welcome back. In this video, we're going to see mathematical induction in action using a simple example. And at the same time, we're going to prove an important formula that we will make use of in later lectures as well. So this is part of the introduction again. And it's called mathematical induction, an example. So the example that we are going to use is a formula that is called the geometric sum. And this formula is the following. So we are going to prove following formula. So here's what we're going to show. For all natural numbers n in n, and all real numbers q that are not equal to 1, the following formula holds. The sum over the summation index k going from 0 to n over q to the power of k is equal to 1 minus q to the n plus 1 over 1 minus q. So that is the so-called geometric sum formula, and that's what we are going to show. A quick example for that, so that you see how that is actually meant. For example, if you have a sum like 1 plus 1/2 plus quarter, that can be written as a geometric sum from 0 to 2 over 1/2 to the power of k. So q in this case is 1 over 2. And according to the formula, that sum would be 1 minus 1/2 to the power of n plus 1, that is 3 in this case. N is 2 here. Over 1 minus q, 1 is 1 minus 1/2. Okay, so this is 1 minus 1 over 8. 7 over 8 over 1 over 2, or in other words, 7/4. And if you look at the left-hand side, precisely what we get here. So this is 1/4, this is 2/4, that makes 3/4, and 4/4 makes 7/4. In this case, the formula actually works. And we're now going to show that it works for all of these cases using mathematical induction. So we'll use a proof by induction over n. And if you do a proof by induction, you should always mention what that number is that you're going to use for your induction. Again, let's write down the statement for general n. That statement is sum from 0 to n q to the power of k is 1 minus q to the k plus 1 over 1 minus q. And now we start with the base case. And again, if you're doing a proof by induction, please always mention what you're using as the base case. It's usually n equals 1, but it doesn't have to be. There could be different base cases, and maybe other base cases are easier to see. So what we do is we take this formula here, and we just substitute 1 for n. So we're using the sum from 0 to 1. This is our n equals 1 over q to the k. Well, what is that? In other words, that is q to the power of 0 plus q, obviously. Q to the power of 1. So q to the power of 0 is 1. So that means what we get here is 1 plus q. Now for the right-hand side, this expression here. Let's compute that one. Oh, I see I'm a mistake here, so that of course should be n and not a k. Okay, so what about the right-hand side of this expression? So write that down as well. 1 minus q to the power of 1 plus 1 over 1 minus q. So again, this n equals 1 enters here. Well, what that is that's 1 minus q squared over 1 minus q. And if you know your binomial formulas, you will recognize 1 minus q squared. That's 1 minus q times 1 plus q. So 1 minus q cancels out, and we're left with 1 plus q. And that's exactly what we wanted. So those two are actually equal. That proves the base case. Okay, that was the easy part. Now for the inductive step. Just copy the statement so that we can have a look at that once again. Now here's the inductive step, and we're doing this from n to n plus 1. So we'll assume that the statement is true for n, and we'll prove it must then also hold for n plus 1. How do we do this? Let's first write down we have what we need to do. So we assume that this statement a equals 0 to n, sum over q to the k equals 1 minus q to the n plus 1 over 1 minus q holds for some n. And we need to show that this assumption implies a statement holds for n plus 1 too. And that statement for n plus 1 that reads sum over the summation index k going from 0 to n plus 1 over q to the k equals 1 minus q to the power of n plus 1 plus 1 over 1 minus q. We want to show. How do we do this? Of course, the first step here is to start with left-hand side. So we take this left-hand side here, and we try to reformulate it in a way that yields this right-hand side. and we need to somehow make use of this statement here. So with sums, it's almost always the same easy process. What we do is we start with that sum from 0 to n plus 1. And this is an easy finite sum. So we can split off any summand we want. In particular, we can split off the last summand. And that's what we're doing. So we split this in two parts. First part is everything but the last summand. The last summand is the n plus first summand. So anything but this summand is this sum here, going just to n, not to n plus 1. And then the last summand is q to the power of n plus 1. Right? So what we do here is we split the sum. Why do we do this? Well, by our induction hypothesis is this assumption here. Let me mark that in color. This assumption here, that's called the induction hypothesis. And we assume this is true. So we have a formula for this sum that goes just to n. We can use that one. So on this part here, we use the induction hypothesis. Meaning we can just use our formula. So this is 1 minus q to the n plus 1 over 1 minus q. And that is true by the assumption that we made. And then we just keep that last part, q to the power of n plus 1. And then let's see if that is actually the correct result already. So let's try to simplify this a little. We just put that on a common denominator. So we have 1 minus q to the power of n plus 1 plus 1 minus q times q to the n plus 1 over 1 minus q. Now if we expand that, get 1 minus q to the n plus 1 plus q to the n plus 1 minus q times q to the n plus 1, that's q to the n plus 2, over 1 minus q. Now you can see that this term here and this term here, those cancel out. So we are left with 1 minus q to the n plus 2. And that is actually the same as q to the n plus 1 plus 1 over 1 minus q. If you look back a little, this part here, so this is exactly the right-hand side that we wanted. So using our assumption, we actually arrived at the correct right-hand side, meaning this is what we wanted to prove. So this proves our inductive step, and that completes the proof of the geometric formula. Now there'll be some more examples in the exercises, of course. As I said, the idea in these simple sum-based inductive proofs is almost always the same. Just split off the last summand and then use the inductive hypothesis, reformulate a little, and hopefully you arrive at the right result. Because there are more involved arguments using this mathematical induction principle, and we might encounter some of these in the course of this semester and maybe the next one. But that should give you a basic idea of how mathematical induction can be applied to prove statements like this. Okay, this concludes our introduction. In the upcoming videos, we'll delve deeper into some of the more involved topics in mathematics. Again, starting from the very beginning, but I hope to pick up pace pretty quickly there. So I'll see you then.